So up to this point, we've studied a lot of different techniques that could be used to solve various varieties of first-order ODEs. But in each of those cases, we did have to be a little bit lucky, and our ODE did have to satisfy some specific condition in order for it to be possible for us to actually find a solution. There are still a bunch more differential equations that are not covered by any of the methods that we've talked about so far. So in this section and in video 14, we're going to talk about some ways to numerically estimate the solution to a differential equation. You can't actually find the solution, but you can get a pretty good idea of the solution's outputs at various locations. This is the kind of stuff that you do when you can't solve a differential equation manually, and because there are so many differential equations that can't be solved by hand, these methods come up quite a bit in practical applications, in particular in engineering and physics. I was on YouTube the other day and I ran across a talk from GDC, Video Game Design, and the speaker was talking about using these methods, Euler's method and RK4, which is from tomorrow's material, to help to try and design a more pleasant feeling jump mechanic in platformers. So this is the kind of method that comes up all the time in practical applications, and that's what we're going to talk about today. Euler's method. So back toward the beginning of the class, we talked about how to take ODE of the form y prime equals some expression containing x's and y's, and we talked about how to create the slope field, a visual representation of that differential equation formed by sketching little baby pieces of tangent line segments all across the xy plane. Now if we had an initial value problem, here's your ODE, here is one point that your solution must pass through, we talked about a way to sketch the solution on the slope field by essentially connecting those little tangent line segments, one piece at a time. Now that's very artistic and intuitive and all well and good, but it's nice to be able to take that artistic process and transform it into an algorithm, for example, to be able to use a computer to do the process. And that's what Euler's method is all about. Euler's method takes this intuitive idea of connecting the tangent line segments and translates it into an algorithm that you can actually program into a computer. So here's the idea. You've got some differential equation, first order, of the form y prime equals some function containing x's and y's. You've also got an initial location which is called x naught, y naught. That is your initial given point, which is on the graph of your solution. So the general idea / pseudocode for Euler's method is to start at the point x naught, y naught, and to choose a real number or a float, which is called h. This is known as the step size, typically. And depending on how you choose your h, depending on whether it's large or small, there are some pros and some cons. Generally speaking, smaller h's give you more of an accurate estimation of your solution. But generally speaking, the smaller h is, the more computation time it will require to complete your estimate. We're going to start from our initial location 0, x0, y0, and then we're going to travel a little bit along the tangent line segment at that location. And it's going to bring us to a new point x1, y1. Then we're going to recalculate the slope of the tangent line, and then we're going to travel a little bit along that line segment, and it'll bring us to a new location x2, y2. Then we're going to travel a little bit along the line segment in that location, and it'll bring us to a new point, x3, y3, and so on and so forth. We're just going to keep traveling a little bit along tangent line segments, constructing a sequence of line segments which is intended to be approximately the same thing as our actual solution curve. Okay, now the beautiful thing about the x-coordinates of these points is that they're all going to be equally spaced. If you want to get to the point called x sub n, all you have to do is start at x sub 0 and travel by your step size h n times. So h is the distance between successive x points. The harder part is getting the y values. The y values have to be found with a recursive algorithm. To find the next y in the sequence, you start by taking the old y, and then you add on h multiplied. Take your step size h and multiply it by the value of y prime at the previous location. So this introduction of y prime in the recursive formula is the aspect of the formula that is causing you to move along a tangent line segment. Now I have debated what kind of software we're going to use to implement this code. This is definitely not intended to be done by hand. This is intended to be done by a computer, to be sure. Now you could use any kind of programming software you want, really. If you're familiar with Python, if you're familiar with C#, C++, I'm sure you can implement this algorithm in any one of those languages. But because you may not be familiar with any programming languages, I've decided to show you how to use this technique on Google Sheets, because Google Sheets is free, doesn't require any programming language knowledge whatsoever, and as a result of Google Sheets' autofill feature, it's actually not that bad to actually implement this recursive algorithm. So that's the program that I will be using to show you how to use Euler's method. Okay, so for example, let's consider the initial value problem y prime is equal to 0.1 times x times y, and we require the specific solution that passes through the point x equals 1, y equals 1. Now, first things first, I'm going to actually solve this differential equation explicitly. That way we can compare the actual solution to the value that we estimate using Euler's method. Okay, so this appears to be separable. So let's separate it. Let's go ahead and integrate both sides. 0.05 x squared plus c. So that means that y would be equal to k e to the 0.05 x squared. Now let's go ahead and let's use the initial condition to determine the value of k. If I plug in 1 for both x and y, it looks like k is going to have to be e to the negative 0.05. So that means that the particular solution that passes through the given point is y equals e to the negative 0.05 times e to the 0.05 x squared. I'm a little annoyed by having both of these e's there, so I'm just going to go ahead and combine them into e to the 0.05 x squared minus 1. This is just a rewrite of the solution, just using exponent properties and some simplification. So now the question says to me, now that you have found the exact solution, calculate the exact value of the solution with x equals 2 plugged in. So I'm going to go ahead and do that. I'm going to plug 2 in for x. which becomes x squared becomes 4. And so y's exact value would be e to the power 0.15 from 3 times 0.05. So here is the exact value of y with 2 plugged in. Let's compare that with what we get by applying Euler's method to estimate the value of y of 2. So here I am on Google Sheets, and what I'm going to try and do is I'm going to try and take Euler's method and implement it in Google Sheets. And the first thing that I'm going to do is, for the sake of reference, I'm just going to fill up a column containing the indexes of all these points that we're trying to find. Start with 0, then I'll enter 1 by selecting the boxes containing 0 and 1, and then click, hold, drag the box on the bottom right to fill in to maybe n equals 20, n equals 21 should be enough. This is mostly for record keeping. So the next thing that I'm going to do is I'm going to try and fill in the column of x's. And to begin with, I was told that my initial x, my x sub 0, the x of my initial point was equal to 1. To fill in the remaining x's, I'm going to try and enter a formula into Google Sheets so that I can again use its autofill feature. And formulas in Google Sheets begin with an equal sign. I am now going to describe to Google Sheets how to calculate the value of x sub 1, the next x value. I'm going to say OK. The step size h was what told me how far apart successive x values were. So if you want to get to x sub 1, take your previous x and add the step size. In our case, the step size was equal to 0.1. H was equal to 0.1. So I'm going to enter that formula in, and Excel says, okay, so that means you need x sub 1 to be equal to 1 plus 0.1, or 1.1. So now that I've established that pattern, now that I've set up that formula, I'm going to click the box which contains the formula, and I'm going to click, hold, drag the box on the bottom right, and that fills in this sequence of x values. Each one of them is one step apart. Now in the problem, they're particularly interested in the situation where x is equal to 2. Estimate the value of y with 2 plugged in. So in particular, looking in the x's column for the location where x is 2, it looks like we're interested in the output, the y value, in the 12th row when n is equal to 10. So I'm just going to highlight that. This value in this yellow box is what we're trying to find. Okay, so the real task now is to fill in the y's column. To fill in the y's column, I'm going to start by entering the initial y, which was given to me. It was also 1. And just like I did for x, I'm now going to try to enter a formula into the next y box so that I can use autofill. So I'm going to try and enter in a Google Sheets friendly manner that recursive formula that I was given back in the general technique section. If you want your next y is equal to the previous y, okay, plus the step size. So that's 0.1 multiplied by the value of y prime, the slope of the tangent line at the previous point. Now the slope of the tangent line in our problem, the formula for y prime is equal to 0.1 times x times y. So I'm going to try and enter in 0.1 times x times y in an Excel friendly manner. So 0.1 will always just be 0.1. But now I'm going to try and indicate to Google Sheets the x of the previous step. So x's are located in column 2. The previous step is located in row 2. So I'm going to click the entry in the second row and second column. 1.1 times x times y. So instead of y, I'm going to click the box that contains the y from the previous step. That y's are located in the third column. The previous step is in the second row, so I'm going to click the box in the third column, second row. So this concludes my formula. Take your previous y and add step size times y prime at the previous x and previous y. Now I'm going to hit enter. And now that I have deliberately taken the time to enter this formula, all I have to do is click that box, click this square in the bottom right, hold and drag down until we pass the box corresponding to x equals 2. So, based on what we have found in Google Sheets, the value of y corresponding to x equals 2 should be approximately 1.1479. Now the actual value of y of 2, calculated with the actual solution that we found, is 1.161834. So not super accurate. The relative error, which is found by taking the difference of the estimated value and the actual value and dividing it by the actual value, is approximately 0.6%. Not especially bad, not especially good. One way to improve the accuracy of the estimate is to decrease the step size. Change the h value from 0.1 down to maybe 0.05. So to reflect that, I'm going to go back to Google Sheets and I'm going to adjust the formulas that I entered for x sub n and y sub n. So in x sub n, we took the previous x and added the step size, which now we're changing to 0.05. So if I then autofill that formula, in order to reach x equals 2, I now need to have n equals 20. I need to step 20 times from the initial location. I'm also going to go into our formula for y, and where we had previous y plus step size multiplied by y prime, I'm going to change that step size from 0.1 to 0.05. So now if I autofill that formula, this time I get 1.158 and some change. Again, not quite perfect, but not completely far off the mark. And this time, if we calculate the relative error, it's gone down to 0.3%. If I take the actual value, take away the estimated value, and divide that by the actual value. If you continue to make the step size smaller, then the estimate will continue to grow more accurate, at the cost of requiring more calculations to actually get that value of y sub n. Let's try it one more time to demonstrate the technique. We've got the initial value problem, y prime equals x squared plus y squared, and we're told that the initial position is going to be x equals 0 and y equals 1. We have a step size of 0.05, and we're trying to estimate the value of y evaluated at 0.5. This is a great opportunity to do an estimate because I'm really hard-pressed to think of any other way that we would actually solve this equation. It's not linear because there's a y squared. It's not even somewhat linear, a Bernoulli equation. It's not separable. Yeah, there's really nothing that can be done here. So this is a situation where I really would be inclined to just estimate this value using Euler's method. So here I am back on Google Sheets, and I've gone ahead and entered in some n values down to maybe n equals 21, and I've entered our initial position. I've entered in that x is 0 and y is 1. Next, I'm going to enter in a formula that I can use to fill in the x values. So I'm going to indicate the previous x value plus 1 step. So plus the step size of 0.05. So let me autofill until we reach the desired x value, which is located at 0.5. We're desiring to reach x equals 0.5. So down we go. And 0.5 is located right here when n is equal to 10. Now our objective is to fill in the y values down to n equals 10. So I'm going to enter the formula equals sign previous y plus the step size h, 0.05, multiplied by the formula for y prime. Y prime was equal to x squared plus y squared. But instead of x, I'm going to click the box that contains the x's from the previous step, the box B2. And I'm going to type in that B2 has to be raised to the power 2 plus y squared. But instead of typing y, I'm going to click the box that contains our previous y values, y to the power 2. Having finished typed in that formula, I'm going to hit enter. Suggested autofill, actually, that's beautiful, isn't it? Suggested autofill, I've selected that and that seems to be a-okay. So let's go ahead and look at the y value paired with x equals 0.5 and the y value is equal to 1.933180859. So that's Euler's method.